Hello, everyone. My name is Jim Elser, and I'm director of the Sustainable Phosphorus Alliance at Arizona State University, and the moderator of this scientific session, Phosphorus and Climate Change, a Vicious Circle. Thanks for joining us. This presentation is one of 3 pre-recorded videos focusing on this important topic before all the panelists come together in February during the live discussion. In this video, Dr. John Downing of NOAA will be discussing important findings about how losses of phosphorus and other nutrients and the associated lake eutrophication that come from them can drive increases in the output of greenhouse gases and especially methane from lakes, thus connecting phosphorus management to climate change. Midway through this video, Dr. Matt Schultz of the Phosphorus Alliance will be joining John to further delve into the connections between nutrient loading and greenhouse gas emissions.
Thanks, Jim. Thanks, Matt. It's a pleasure to be involved in this great panel on phosphorus, my favorite element. Back behind me, you see Lake Superior that has almost no phosphorus in it, but I work on it there anyway. Today, what I'd like to do is to talk about 3 different things. First off, I want to talk about how lake phosphorus enrichment, what I'll call eutrophication, it pretty much interchangeably drives greenhouse gas emission and therefore climate change. And the greenhouse gases we'll be talking about today will be carbon dioxide, methane, and nitrous oxide, sort of the classic gases. Then I want to move to, because we will find out that phosphorus enrichment drives greenhouse gas emission, we'll move on to looking at how much nutrient enrichment is going to increase in the future, in the near and longer term future. And then finally, we'll end up by thinking about the social impact of that, social and economic impact of global climate change on health, welfare, well-being of people on the planet. First off, we were really interested, a couple co-workers of mine and I, in trying to figure out how greenhouse gas emissions were driven by phosphorus concentrations. And this became possible. This is work with Tonia Del Santro and Jake Beaulieu. And we became aware that there was enough improved sensor technology that we're getting lots of local estimates, and we felt that we could use this to estimate the role of phosphorus enrichment on greenhouse gas emissions from lakes and what you might call ponds. We did this in a pretty straightforward secondary analysis kind of way. We gathered together 8,000 worldwide estimates of including CO2, methane, and nitrous oxide concentrations and emissions from the published literature. And then I did some simple linear and multiple regression with lake size, phosphorus, and chlorophyll concentrations to look at the trophic effect of phosphorus and chlorophyll on emission rates. And then we did a globally weighted total emission calculation by using weighting by lake size and productivity. And the productivity distribution was inferred from satellite measurements, distributions of chlorophyll concentrations, and the lake size distributions came from several different works using different methodologies. The flux findings were the findings about how flux varied with nutrients were quite straightforward. The 2 big variables were lake size and trophic status driven by phosphorus concentration. And I'll really concentrate only on the one that you're seeing here in this image, and that is methane emission, and that will be shown in a couple of minutes here to be disproportionately important to the other greenhouse gases in terms of eutrophication-driven greenhouse gas flux. But carbon dioxide emission was also influenced both by phosphorus concentration and lake size, and as was nitrous oxide. But generally, what we saw, the really striking result, was that methane emissions increased really sharply with increased phosphorus and chlorophyll concentrations in lakes, and that would allow us then to do a trophic weighting or a phosphorus weighting to calculate based on satellite estimates of phosphorus and chlorophyll distributions worldwide what the overall emission rate was for all lakes on the planet. And generally what we found was that phosphorus and lakeside weighted estimates were really nice, robust predictors, much more robust than other predictions that have been made or calculations that have been made, and that a really phenomenal amount of emission of CO2 and methane, both considering diffusion and ebullition, bubbling methane, and nitrous oxide, these were fairly large amounts. And just for comparative purposes, the methane emissions alone are something like an order of magnitude higher than that from all of the world's oceans, just to give you an idea of how big the current methane emissions are. And then what we could do is use those using various measurements to calculate the atmospheric impact of emission of those greenhouse gases to the atmosphere. And what we found was that about 3/4 of the impact was due to methane emission, even though methane was not the major source of carbon coming out in gaseous form from lakes. It was very impactful because it's highly atmospherically active. So just for comparative purposes, all carbon export to the atmosphere from lakes is about 1.5 times the carbon burial found in all of world oceans, and about 1/3 of the carbon delivered annually to oceans from rivers. So very large amount coming from inland waters. The atmospheric effect of greenhouse gases from lakes is currently something comparable to about 20% of the effect of global fossil fuel burning and the emission of CO2 and other gases to the atmosphere. So the atmospheric impact of lakes is about 3/4 due to methane, and carbon emission to the atmosphere is about only 10 to 15% methane, but atmospheric impact of carbon dioxide is small, but the effect of methane is large. And if you think back a couple of slides, methane is very strongly driven upward by phosphorus emission and phosphorus concentrations. So Tanya Del Santro and Jake Bollier and I then thought it would be really interesting to project out eutrophication to 2050 and 2100 to get some idea of how the atmospheric impact might change as eutrophication is altered on the planet. So the projected changes in phosphorus and nitrogen losses to waters by 2050 and then 2100 are pretty large, but these are mostly, as you might expect, phosphorus driven, because annually each person kicks out about a little bit less than a kilo per capita of phosphorus. And when you look at the population growth on the planet, it's very fast and very large, and obviously is increasing phosphorus in effluents. So the projected changes that we saw were due to things like population growth driving river nutrient export, phosphorus runoff due to increased food production demands, agricultural phosphorus losses, extrapolation and modeling of phosphorus mining data, manure and urine export from increased meat demand by increasing populations, and population growth without considering utopian assumptions and some guesses about how population might grow under different conditions. Importantly for phosphorus, if you look at how much it is likely to increase by 2050 and 2100, it's likely to go up by something like 1.5 times as a minimum to 3 times by about 2050. So fairly large projected increases in phosphorus. Now, those phosphorus emissions will be treated in different ways as they're dropped on the soil or lost from the soil. We should multiply those, use some multipliers of those phosphorus effects on eutrophication-driven methane emission. And one important one is that climate will drive up nutrient mobilization very effectively due to storms, due to runoff, due to phosphorus delivery. And that should augment or multiply those effects of phosphorus by 10% to about 20%. Increased primary production per unit of phosphorus due to temperature increases should go up by about 30%, and increased spatial extent of inland waters will go up by about 10%, pretty conservatively, unless really wonderful things happen and we get ourselves under control. So we should be expecting freshwater eutrophication to increase fairly dramatically. By 2050, we should expect eutrophication itself, driven by phosphorus release, augmented by warming, increased storms, and climate expanded lake area, to 1.3 to 3-fold by 2050, and to 5-fold, shockingly, by 2100. And these will be the drivers of greenhouse gas release from lakes, and that will be driving up these methane emission rates from aquatic systems as lakes become more eutrophic due to phosphorus emissions, phosphorus losses. So when we compare future lakes' atmospheric methane impact to other sources and sinks, it puts them in perspective. We should expect methane impact of eutrophied waters to be about 1/3 of fossil fuel burning and more than that of land use change. We'll be expecting these emission rates to counterbalance the atmospheric effect of all oceanic carbon burial and of annual burial of global soils. So fairly large impacts of eutrophication driven by phosphorus. we wanted to know what this really would mean to people, and so wanted to convert these to social valuations. And in this work, I was joined by three excellent economists, Sheila Olmstead, Steve Newbold, and Steve Pulaski. We worked together to do a thing called integrated assessment of economic value and cost, which calculates the present value of avoiding damage or the cost it will create, which is essentially, you can think of this as the amount of money you'd need to put into investments now to pay for future damages. To cut to the chase, these costs will be rather gigantic. So the global cost we're projecting based on, depending on interest rates and rates of increase, would be in the range of 6 to 90 trillion US dollars for phosphorus pollution's future economic and social cost. Now, social cost comes from a variety of different sources. Of course, that would be things like health effects, impacts on settlements, sea level rise and coastal damage, catastrophic impacts due to extreme storms, impacts on vulnerable markets like agriculture and forestry, and so on. So 6 to 90 trillion dollars in effect of eutrophication into the future. So global greenhouse gas effects also affect local costs. When we used Lake Erie as an example, we found that the global cost of phosphorus-driven methane from Lake Erie was 1 to 2 orders of magnitude higher than the local costs of the impacts of eutrophication on fishing and beach use. So what this means to us is that when we control or reduce phosphorus emission, we win twice. We win at home by having better water and better water to use and to enjoy, and we win globally by decreasing climate damage costs by a minimum of something like $6 trillion by the year 2050. So to summarize then, phosphorus pollution is a powerful driver of greenhouse gas emissions from lakes, and these are really dominated by methane emissions. They contribute about 3/4 of the atmospheric climate impact of lake phosphorus pollution. Phosphorus and nitrogen pollution of lakes will increase very much, 1 to 3-fold by 2050 and 2 to 5 times by 2100 unless things change radically. The atmospheric impact of phosphorus pollution of lakes will be greater than that of land use change, will counteract oceanic and terrestrial carbon sequestration, with a social cost to humanity on the planet in the range of 6 to 90 trillion US dollars. This means, in grand summary, it's important to protect lakes from phosphorus pollution and reverse it if we can. I thank you for listening and thank you for your time.
Thank you, Dr. Downey. Now Dr. Matt Schultz from the Phosphorus Alliance will join the conversation. Welcome, Matt.
Well, thank you very much for that talk. This is Matt Schultz with the Sustainable Phosphorus Alliance at Arizona State, and I'm going to be handling the respondent questions for these sections. I guess the first question I have for you is, do you have any sense of how much our current greenhouse gas emissions can be attributed to past eutrophication versus how much was there without eutrophication, I guess?
You mean sort of a natural eutrophication, Matt? Is that what you're, yeah.
Yeah, sort of segregating out what are we to blame for versus what would just be there naturally.
Yeah, it's, I worked for 20 years in the state of Iowa working on eutrophic systems, and it's always a tough question to backcast where these systems were in the past in terms of how much phosphorus they were actually receiving. I would say that probably in those highly eutrophic systems that are probably responsible for most of the methane emissions, we're talking about something like 2/3. And this comes from some work on coring and rebuilding phosphorus history in those systems. So, you know, probably 2/3, 3/4. The history of eutrophication and phosphorus pollution goes way, way back and was noticed essentially as soon as settlements became dense. And so it's a long-standing issue on the planet. But I think in areas that are intensively farmed and those receiving non-point source pollution, as well as a residue from point source, it's probably in the neighborhood of 2/3 to 3/4. I mean, that's a sort of back of the envelope calculation.
And just to be clear, 2/3 to 3/4, that's the amount owing to human-caused
Human,
eutrophication, right?
exactly.
Yeah, okay,
Right.
great,
Yeah.
great.
Right.
Great, thanks. And so what about coastal eutrophication and its effects on greenhouse gas production? Would you expect the same methane flux changes there as well?
I would. The global work on the oceans seems less far advanced than inland waters. There's a lot of ocean out there to work with and a lot of variation in oceans. But the recent work that's been done on methane emissions shows really strong concentrations of higher methane emission rates near shore or in the coastal zones. It's very strongly correlated with water depth, and I think that's probably because of methane oxidation as it moves up the water column. That would be my guess. So some great work by Weber and co-workers that's recently been published shows that. And I showed briefly a number of, just saying basically how does freshwater methane emission compare to oceanic, and it's an order of magnitude lower. And when you consider the huge amount of ocean, it's remarkable that the aggregate methane emission is so low compared to inland waters. Mind you, these are inland waters are enclosed. They can take pollution up to or take phosphorus concentrations up to much higher concentrations.
Sure.
So, but I think there's a real high potential for it there, Matt, for methane emission in the coastal zones.
Yeah, and just one more quickly. So we have a current greenhouse gas protocol, and this is a way that if you're a municipality or a food producer or someone like that, you want to measure and report your greenhouse gas footprint, you use these protocols to help guide the calculation. But there's no real way right now within that protocol or other protocols to connect, phosphorus pollution, nitrogen pollution to greenhouse gas emissions. That would seem to be a way that you could drive change because a lot of folks are reporting these emissions and calibrating their efforts according to them. So what would it take how difficult of a task is it to sort of peg these phosphorus emissions, nitrogen emissions to greenhouse gas emissions in particular water bodies?
Yeah, what it takes is the kind of work that Tanya and Jake and I did, and that was to collect the data together and try and estimate the effect of nutrients on the emission rates. And constrain those better and better over time. The tighter confidence intervals we have around those numbers and those predictions, the better off we are. We do have models right now that anyone can use on any size of lake. And the central tendency on them will probably be right, but maybe the confidence interval will be large. They'll be not so well constrained. But I'd say any community who wants to know what the global impact of allowing more eutrophication, or as you suggest, decreasing eutrophication might have on atmospheric emissions, it's quite simple calculation to do. Lake size doesn't seem to have any effect. So the models will work on small and large lakes and give us at least an estimate of central tendency.
Great. Thanks so much for your answers to those questions. And I'll turn it over to Jim now.
It's a real pleasure. Thank you, Matt.
Thank you again, John, for your presentation, and Matt for the great discussion. Just a reminder to everyone that this is just one of 3 spotlight videos focusing on the work of these speakers on this topic, before they all come together in February in the live panel dealing with phosphorus and climate change, a vicious circle. Please check the AAAS annual meeting website for the panel's date and time. Again, thank you, John, thank you, Matt, and thank you to the audience, and we'll see you live in February.